Okay, so we were in the middle of showing that the heat kernel on the circle is a good one. Let's do that. Okay, so let's recall. Okay, let's recall what we were talking about. We had this thing, the heat kernel on the circle. Right. Which was summation over n in the integers, e to the negative 4 pi squared n squared t, e to the 2 pi I and x. Okay, and then we also had the heat kernel on the line. That was squiggly h. Maybe I should use the cursive h. It's the same thing. Which was the dilated Gaussian. So 1 over the square root of 4 pi t, e to the negative x squared over 4t. Okay, and we saw last time that there was a relation between the two that we got by using the Poisson summation. That was that the heat kernel on the circle was just the periodization of the heat circle on the line. Right. So this was it. Okay. Right. And the nice thing was that we were able to use this to get that the heat kernel on the circle was an approximation of the identity. Okay, so we're in the middle of this theorem that HT is an approximation of the identity. Okay, right. So, and the thing that we needed to show was the last part, that that the heat kernel on the circle gets bunched up near the center as t goes to 0. Right. So we needed to show that given any, wanted to show that for any eta less than a half, that well, in any case, that the heat kernel gets bunched towards the origin as t goes to 0. I'm not gonna write it out. Okay, and the trick was to use the Poisson summation formula, and recognize that the heat kernel on the circle is just the heat kernel. For n equals 0, we get the heat kernel on the line, right? So we can realize this guy as the heat kernel on the line plus some error. And we already showed previously that the heat kernel on the line was a good kernel. So all we have to do is show that the error goes to 0 as t goes to 0, right? So the idea was express ht of x as ht x plus 0, right? And then all of the other terms, n not equal to 0. Ht x plus n, where n is not equal to 0. We call this thing the error term, e sub t x. So this thing we're going to call e sub t of x, and we'll see that right. Our claim is that that as t goes to 0, we have this as t goes to 0, et of x also goes to 0 uniformly in x. Okay, so we have this uniform bound on the e sub t's as t goes to 0, and so that that does it for us. Okay. 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 So so let's look at that. So consider e sub t of x, right? That's the sum of the heat kernel at all these other points, right? So it's sum over n not equal to 0, 1 over root 4 pi t, e to the negative x plus n squared over 4t. Right, yeah. Okay, so, so the first move we're going to make is to say, well, this x, we're gonna basically get rid of the x, and right, because the thing is that right, we're on the circle that is the unit interval from -1/2 to 1/2. So x is small, right? So x is smaller than 1/2, right? And n is 1. N is in absolute value bigger than 1, right? So that means that x plus n is going to be smaller than 3/2 absolute value of n, and greater than 1/2 absolute value of n, right? So this x plus n squared term, we can basically replace with n. Okay, right? So yeah. So since this is true, we see that that E of t is controlled by summation e to the negative n squared, some constant c n squared over t, and then we have this we have the 1 over we have basically c over root t here. So the first move is that we can ignore the x, right? We can ignore the x. Okay. Okay. So so now we want to show that thing that thing goes to 0. This thing goes to 0 as t goes to 0. Okay. So the trick is to split this thing, split this n squared over t. Okay, so for small, we can assume that t is between 0 and 1. T is between 0 and 1, right? So in that case, n squared over t is going to be bigger than n squared, right? Because we're dividing by something smaller than 1, right? But we also have that n squared over t is bigger than 1 over t, because n squared bigger than equal to 1 over t, because n is in absolute value greater than 1, right? So so we can say that n squared over t is bigger than or equal to the average of those two things, right? 1 over t and n squared. Okay, right. So that gives us a way of pulling out, separating the n squared from the t here, right? So so this thing, right, is going to be less than or equal to c with square root of t summation n not equal to 0, e to the negative c over 2, 1 over t plus n squared, right? But now we can pull out the 1 over t terms. right? And we get that this is, so this thing is equal to c over root t, e to the negative c over 2t, summation n not equal to 0, e to the negative c n squared over 2. Okay, and that does it for us, right? Because this term, this term is finite. It's just some constant, right, independent of t. And as t goes to 0, well, this is also going to go to 0, right? So this goes to 0 as t goes to 0. Hey, Jay. So, and that is the proof, and that is the proof that the good kernel is actually a good kernel. Let me just sketch out, because you're here. So let me sketch out what the point is here. Okay, so right, so this is the error term, right? We wanted to show that the Heat kernel on the circle was a good kernel, and we said, okay, well, the Heat kernel on the circle is the Heat kernel on the line plus this error term, right? So the main what we want to do, the Heat kernel on the line is already a good kernel, so we just want to show that this vanishes as t goes to 0.
Yeah.
Right. Okay. So there's basically two tricks involved. One is first is you can throw the x out, right? You can throw the x out because x is between -0.5 and 0.5, right? And n is bigger than 1 in absolute value, so x plus n is trapped, is basically n, right? You can basically ignore the n because it's smaller than half. You can ignore the x because it's smaller than half of n.
Yeah.
Okay. So adding it on doesn't really change n. Okay. So you say, okay, now we've got this sort of expression, right? We can get rid of the x, and then at this point you play this trick. You say, well, we're going to separate. We got this n squared over t. We're going to separate the n squared and the 1 over t by saying, well, look, the n squared over t, right? Assume that t is small. N squared over t is bigger than n squared, right? But n squared over t is also bigger than 1 over t, right? So n squared over t is going to be bigger than the average of those two terms, right? And so that allows you to that allows us to replace the n squared over t with this split term, right? Once you split the term, well, then you can pull this constant out. Right, you pull this constant out here, right, and then you're left with this term, which is just a finite sum, right? This is just a finite sum, and then as t goes to 0, this goes to 0, and that's it. Yeah. Okay, so that's why it's a good kernel. Okay, okay, so that's. Now we're going to talk about the Heisenberg Uncertainty Principle. Okay, so Heisenberg uncertainty. There's kind of two ways of looking at it. One is this quantum mechanics way. So you have a particle, and then you have this thing called the state function of the particle. And it's something of L2 norm 1. And so the state function gives you certain information. It says that the probability of the particle being in a certain interval AB is the integral. It's just the integral of of the square of the function over the modulus squared over that interval. Okay, so that's the probability. Okay, and then the right. So this is like the then the expected position is going to be the integral of x x times that over all of r. Okay. Okay. So that's denoted by x bar. It's like the average basically. And then so on the other hand, we've got momentum, where the oh sorry, I should say we also have this thing called the variance, which is basically measuring how much you deviate from the expected position, right? So you got this sort of thing. Okay. On the momentum side, you have something analogous that the.
Is there no square for the x minus x bar?
Oh, I'm sorry, there should be a square. Okay. Okay. So on the it turns out that the momentum is the Fourier transform of the state. The state function for the momentum is the Fourier transform of the state function for the position, and so you have something similar, right? That you've got the expected momentum. Right, you've got it's the same sort of thing. You've got the expected momentum, and you've got the chance of the momentum being in a particular interval. It's just the Fourier transform of that. The expected momentum would be you just use the Fourier transform here, and the variance of the momentum, just take the Fourier transform there. Okay. Okay, so that's one way of looking at it. The other way of looking at it is in terms of signals, time and frequency. Okay, so right, this is basically like if you look at a signal, right? You can think of this as like the signal which has L2 norm 1, right? Then like the chance of the signal being in a particular time interval is just the integral of this thing of the signal over that time interval, right? Right, and this is sort of like the average in time of the function, right? And then on the other, the Fourier transform is going to be the frequency, right? And so you can talk about like the variance of the variance of the time and the variance of the frequency. Okay. And so what Heisenberg uncertainty says is that you can't localize both position and momentum simultaneously, or in the other sense, you can't localize the function in time and frequency simultaneously. Okay, so it's localized in time, then you're not localized in frequency. Okay, so properly speaking, it's this sort of thing, that the variance of the position slash time times the variance of the momentum slash frequency is always bigger than some constant. Right. So if you know the position very precisely, then the variance of the momentum must be great, and similarly for time and frequency. Okay.
The way the book has it is it's not specifically deviation from the mean, but rather from any x0.
That's right. That's right. Yeah. Yeah. So
does that make a difference? So.
No, it's I think it's equivalent actually. Like
Oh, okay.
yeah. Yeah, I think. Yeah, so the way they showed in the book is they say, well, that's going to be, that number is minimized at the mean.
Okay.
Yeah.
Okay, yeah, that makes sense, yeah.
Yeah. Okay, so here's the statement that the book gives. Suppose you have a Schwartz class function of L2 norm equal to 1. So they prove sort of a particular case first, and then they show that implies the general case. They say, okay, that if you look at x squared psi of x squared dx times the integral of c squared for a transform of c squared dc, then that's always bigger than 1 over some constant times 1 over 16 pi squared. And that in fact, this is true for, it's true if you look at x minus x naught. C minus C naught squared. For any for any x naught and c naught. Okay. And that this is minimized when x naught equals x bar and c naught equals c bar. And also that equality holds. And that equality holds if and only if C is some sort of Gaussian function. Okay, so like the Gaussian is sort of like the best you can do for if you're trying to localize in time and space. I mean in time and frequency. Okay. Yeah.
Will this just happen to be because it is its own Fourier transform?
Let's run through it and let's see. I'm not sure if that's exactly why. That is, there are other things that people have created over time that are also good, and I don't think those are their own Fourier transforms. But they're they're not. I mean, they're not as good as the Gaussian, but they are like pretty good. So, well,
It makes sense because then both the terms in the integral are the same, so.
yeah.
So then. And like, it's 1/4 pi squared. But yeah.
Okay. Okay. So let's prove it. So the proof just follows from the fact that so you start off. You say, well, look, the L2 norm is 1, right? So that means that the integral from negative infinity to positive infinity of the absolute value squared is 1, right? We do an integration by parts on it. We we basically pretend that there's a differentiation of a function in there, right? And so we pass the derivative from the x. We put in a 1. The 1 is the derivative of x. We pass the differentiation onto the other guy. We get negative x times the derivative of this product, right? So that's going to be pi of x, pi bar of x, pi of x bar plus x, pi prime x bar, pi of x dx. Right? So just integration by parts. If we take the absolute values, and use the triangle inequality, right? So this is less than or equal to twice absolute value of x, c of x, c prime of x dx. Right. And then we use the Cauchy-Schwartz inequality. So we say, well, that's going to be controlled in turn by the x squared c of x squared dx to the 1/2 times the L2 norm of this guy. The L1 norm is controlled by the product of the L2 norms. Cauchy-Schwartz inequality. Okay. And now by Plancherel's theorem, this is the L2 norm of the derivative. We can switch that to the L2 norm of the Fourier transform of the derivative, right? So that turns into this term here turns into 4 pi squared times the L2 norm of the Fourier transform. Times c squared. Right. And so that gives it to us, right? That's the end. Right. We get that right, that the product of the variances is bounded below by some constant.
why would anyone ever write that constant as some constant times 1/16 squared when it's clearly off? Or am I missing something?
Oh yeah, what was that? What was that about? So they've done here. They've squared both sides. We get 8 pi squared. It's just going to be 1 over 8. It's just 1 over 8 pi squared. No, 1 over.
Oh no.
No, 1 over 16 pi squared. It is 1 over 16 pi squared.
Yeah.
But why did I put this thing in? It's just 1 over 16 pi squared.
Oh, the camera was blocking the 4 pi squared.
Ah, sorry. Okay. Yeah. Okay, so that is the Heisenberg Uncertainty Principle, and then to get the other part, so if you apply it to if you apply it to c of x plus x squared times e to the negative 2 pi I x x c naught, then you get the shifted version. You get this version.
Yeah.
Okay. And so the only thing that's left is this to show that when equality holds if and only if it's a Gaussian function. And for that, you use the Cauchy-Schwartz inequality. So, right, so Cauchy-Schwartz says that Cauchy-Schwartz says that you'll have equality when the functions are multiples of each other. So that would mean that C prime is some constant times C. Some constant times times the other function, right? We've got this function and this function. We say that the L2 norm of this guy. The L1 norm of the product is controlled by the product of the L2 norms, right? And Cauchy-Schwartz says that for this to be an equality, these must be a multiple of the other. One must be the multiple of the other. But that immediately gives you that it must be a Gaussian, right? Because then you get that C prime over C must be beta times x, right? Which tells you that C must be some constant times e to the beta x squared over 2. And then that's basically yeah. Okay. So okay. So yeah, that's the end of that chapter. So the next chapter is doing the Fourier transform in higher dimensions. So Fourier transform on RD. So let me just put down some notation first. So if we have a vector in RD, and then we have some alpha in ZD, so alpha is going to be just some tuple of integers, right? Then we define x to the alpha is defined to be x1 to the alpha 1, x2 to the alpha 2, xn to the alpha n, xd to the alpha d, excuse me. Okay, so it's just like the multi-index. Okay, and then when we write ddx to the alpha, that is, as you can guess, ddx1 to the alpha 1 to ddxd to the alpha d. We're in RD. We're in d-dimensional space. One thing that's going to be important is rotations. So let's recall that if you have R, a matrix going from RD to RD, so a linear transformation. So R is a matrix. It's just a d by d matrix. Left multiplying gives you a map from RD to RD. If R times R of a vector dotted against R of another vector is always equal to the dot product of the original vectors, then we say R is a rotation. So you see that what it does is it preserves the angle, or preserves the angle between the two vectors. Right. So this is that it preserves angles. Right. And just kind of a so Rx. Thinking of this as a matrix, and this is some vector, Rx dot Ry is the transpose of Rx times Ry as as vectors, right? Which is the same thing as x transpose R transpose R y, right? So what this is saying is that that R transpose is going to be R inverse, right? That R transpose is R inverse, so that you end up with x transpose y, the dot product of them. Okay, so right. So in particular, the determinant of R is going to be 1. Because R is a subtranspose, right? And I'm not sure if this is important, but in any case, the absolute value of the determinant is 1, right? The absolute value, because you know that the square of the determinant is 1. Yeah. If the determinant actually is 1, it's called a proper rotation. And if it's -1, then it's called an improper rotation. Or I'm sorry, if it's not equal to 1, then it's an improper rotation. So basically, it's like, does it preserve the orientation? Does it reverse the orientation? Okay. So just as before, we have the idea of rapidly decreasing functions. So if you have some function, and it's continuous, so from RD into C, if you know that x to the alpha f times f, for whatever alpha is always bounded, right? So if for all alpha in z to the d, this thing is bounded, then we call it rapidly decreasing, right? If if the absolute value of x to the d plus 1 f of x is bounded, then we call it moderately decreasing. Okay. More notation. More notation. So recall in R2, right? You can express an integral. You can express an integral. You can change a Cartesian integral into a polar integral, right? The integral of f r cosine theta r sine theta r dr d theta, right? S theta goes from 0 to 2 pi, and r goes from 0 to infinity, right? So you've got polar integration. We're gonna use this notation, so we'll notate g of gamma d sigma gamma over S1 as this integral over the integral with the circle. Okay. So g of cosine theta sine theta d theta. Right. So this is sort of just a notation, and in that case you can rewrite this. You can think of this as the integral as of f of r gamma r dr d sigma of gamma as gamma ranges over S1. Okay. So and you do something similar in higher dimensions. So in R3 you've got spherical integration. You use a similar change of notation. And in general, you have this polar integration over space. You integrate over the over the sphere in RD, right, and then let the radius, right, so d sigma gamma, right, gamma ranges over the sphere, and you integrate over as r goes from 0 to infinity. This time, of course, you get r to the d minus 1. F of r gamma. Okay. So this is a formula that we're going to use a lot. Changing the integral over this into RD into this spherical integral.
Is the
Yeah.
d sigma gamma supposed to evoke some sort of idea that you're integrating over the group?
So yes, so actually, so I'm introducing it as a notation because that's kind of effectively how we're going to be using it. But in reality, this is a measure,
Yeah.
right? This is actually a measure on this on this surface,
Okay.
right? And then you're integrating with respect to that measure. Yeah, but effectively, it's the same thing as saying something like this.
And it's all okay because SD1 minus 1 is like locally compact, but
Yes.
not abelian with reflections, right?
Oh, I mean, what? This is you don't have to think of it as a group. It's rather simply you're integrating over a manifold. Integrating over a surface. Yeah. It's not nothing deep. Yeah. Okay. Okay. So let me just do one last thing, which is that for f in the Schwartz class, for f in the Schwartz class, right, so we define the Schwartz class on d-dimensional space in exactly the same way, right? We say that as long as the supremum of x3 alpha ddx beta f of x is bounded, right, for all multi-indices. Right, so now we need multi-indices. As long as this is bounded for all multi-indices, then the function's in the Schwartz class, right? And then you define the Fourier transform in kind of the obvious way. And then I think one interesting thing is one thing that's going to be useful for us is that if you take if you start off with your function and then you create another function which is the rotation, you rotate the input before putting it in here, right? If you take the Fourier transform of that, then that just turns out to be that turns out to be the rotated Fourier transform, right? So the Fourier transform of the rotate function is the rotated Fourier transform. Okay, and that is just a calculation. You say, well, look, this thing on the left is f of Rx e to the negative 2 pi I x dot c. Right. But then doing a change of variable, you get f of y, right? Let y be the rotated. Let y be r of x. Right. Then this is going to be e to the negative 2 pi I x, which is y rotated in the opposite direction, dot c dc. Right. Then you can pass the rotation on to the other guy, right? Because r inverse y dot C is y, y transpose R inverse transpose C, right? So you can pass
R inverse is R transpose.
yeah, R inverse is R transpose, right? So you get just R arc C, exactly. Right. Oh, I forgot. We need the Jacobian. Right, but the Jacobian is 1. Right, and then that's it, right? So you get Fy e to the negative 2 pi I y dot arc C dy, which is the Fourier transform at R of C. At R of C. Okay. And this property is going to be useful when we talk about the Random transform.